If you write a basic computer program, the instinct is to write a single, continuous list of instructions, read top to bottom, executed sequentially. But as software grows to thousands of lines, that linear structure collapses under its own weight. Finding a single logic error in a massive block of code is incredibly difficult. And when multiple developers need to work on the exact same file simultaneously, their changes overwrite each other, creating logic conflicts. The biggest cost, though, is repetition. If you need to perform the exact same task, like verifying user data, in 5 different places, a linear script forces you to write the exact same code 5 separate times. Fixing this requires stepping away from continuous scripts and moving toward functional isolation. Code needs to be broken apart into specialized, self-contained units. Professional software architecture is designed so that machines can run it, but more importantly, so that human developers can actually read, maintain, and expand it safely. In C++, the tool for this isolation is the subroutine, or function. It is a strictly quarantined block of code designed to execute exactly one task perfectly on command. To modularize a program, developers first scan their existing codebase to identify any repetitive logic patterns that can be extracted. Looking at this diagram on the left, we see a monolithic code block. The highlighted sections represent redundant logic scattered throughout. By shifting right, we see those redundancies extracted into distinct modular puzzle pieces, functions dedicated to initialization, processing, or data transformation. What remains is a primary control script that is almost completely empty of raw logic. It simply calls these reusable units exactly when their specialized action is required. Subroutines take a fragile, linear tower of instructions and turn it into a highly resilient puzzle of interlocking, isolated logic. Before a subroutine can be used securely, the developer has to define its rules of engagement using specific C++ syntax. This blueprint outlines the 4 anatomical requirements of every C++ function. It dictates the return type, a unique function name to act as an identifier, the incoming parameters, and the central logic block. To understand data flow, we compare parameters and arguments. The baseball pitcher represents the main program, throwing an argument, a concrete numerical value, like 4. The catcher's mitt represents the parameter, a local variable container built specifically to catch incoming arguments. Once the function processes that data, it must handle the output according to strict categories. This table classifies functions by return behavior. On the left, void functions execute actions, like printing text with no return value. On the right, non-void functions process calculations, requiring a specific data type and an explicit return keyword to send results back. Establishing this input and output contract ensures data flows predictably across different scopes of the application. Defining the function is only the setup. Executing it actively alters the control flow of the entire application. Inside the main program, the system reaches a call for Tamba. Immediately, values 3 and 5 are transmitted across the scope into the subroutine's parameters, where it executes its isolated calculation logic. While calculating, the main program halts in suspension. Once complete, the result is ejected via the return statement. The value 8 travels back to the main program, and the subroutine's memory clears. This continuous cycle of pausing the main thread, passing data, processing, and returning results is the mechanical heartbeat of modular coding. When handing data over to a separate subroutine, the main program needs a way to guarantee its original variables aren't accidentally destroyed or corrupted. C++ protects data using a default behavior called pass by value. As this visual analogy shows on the left, passing by value is like keeping your original document locked in a safe and handing someone a disposable photocopy. The subroutine can manipulate or destroy its duplicate copy, while the original variable remains safely untouched. However, to permanently update original data, developers use pass by reference, acting like granting multiple users edit access to a single shared cloud document. To enable shared access, the developer alters the syntax. This chart shows the specific trigger, an ampersand symbol next to the parameter. This tells the system to bypass duplication and grant direct access to the original memory address. Deciding whether to pass a value or pass a reference forces the programmer to balance raw operational speed against strict memory safety. When hundreds of these completely isolated functions operate together in a single system, they create a comprehensive software ecosystem. Complex applications rely on a central nervous system to intelligently route traffic, delegating operations to highly specialized satellite nodes. This architectural map demonstrates that structure. A main controller sits in the center, managing the flow of data out to independent modules, like a calculator suite, a payroll processor, or an exam grading system. Because each node communicates only through its strict input and output contracts, developers can update the payroll module's math logic without risking a catastrophic crash in the main system. Building software professionally requires stepping back from individual lines of code and architecting complete, self-sustaining networks. We can apply this architecture directly to a practical STPM-level coding scenario, calculating an exam average. This final code schematic maps the exact relationship between the main block and the Cura-Parada subroutine. The main program block on the right initializes 3 separate test scores locally. It then pauses its execution to call the function, passing those 3 distinct variables as arguments. Inside the subroutine's isolated memory frame on the left, the parameters receive the values. The logic adds them together and divides by 3.0, specifically utilizing a float data type to preserve any exact decimal results. Finally, the return statement fires, ejecting the calculated average back across the boundary into the main block, where it is immediately outputted to the user. Mastering the use of subroutines marks the transition from writing linear, rigid scripts to engineering secure, highly scalable software architecture.